Hello guys, and welcome to my YouTube channel. My name is Simona, and today we're going to be going over a hydrogen NMR example. The formula we are given is C3H7Br. So just expanding it a bit, step number 1 is always to solve for the DBE, so the double bond equivalence of the molecular formula. So I want to know the double bond equivalence of C3H7Br. The formula is as follows. So it's 1/2 bracket 2 times the number of carbons plus the number of nitrogens minus the number of atoms that make one bond. So this would be the hydrogens and the halogens. So hydrogens or the halogens. So I could just use the letter H. And then plus 2, which is like a buffer. So here, it would be equal to 1/2 and then 2 times the number of carbons. So there's 3 carbons, 2 times 3. And then number of nitrogens, there is none, so plus 0. And then minus the number of halogens or hydrogens. So 7 plus 1 is equal to 8, so minus 8. 7 hydrogens and 1 bromine equals 8. And then plus 2. So this would be equal to 1/2. And then if you add up everything in the brackets, you have 6 minus 8 plus 2. That is going to be equal to 0. So the number of double bonds is 0. And this is good to know before we attack the actual spectra. We want to know as much information about our product before we start. So right now, all I know is that, okay, well, there's 3 carbons. And since there's no double bonds, what does that tell me? I'm probably dealing with propane, just an alkane chain of single bonds between the carbons because there's no double bonds. So this already gives me pretty much a structure, and I'm gonna just have to figure out where to put the bromine. So now, after I determine the double bond equivalence, the next thing I want to do is perform IMP on each of the peaks. So I already gave you the I, so starting with the pink one, I'd go IMP, and what I stands for is integration. Let's bring this to another sheet. IMP. I is equal to the integration. M is equal to the multiplicity. And then P is equal to the ppm. So the integration is equal to the number of hydrogens. The multiplicity is going to give you insight into the number of neighbors. Number of neighbors. And then the ppm is going to give you insight into the region. And the region corresponds to electron richness or electron poorness. So these are 3 things to know. Okay, coming back to the hydrogen party. So integration of 1 for the pink region. What does this mean? Well, it means we're talking about 1 hydrogen. So this would be an H. So this is literally just 1 H. H. So now if you want to ask, okay, well, how many neighbors does this hydrogen have? We have to look at the multiplicity. So counting the number of little mountains, 1 mountain, 2 mountain, 3 mountain, 4, 5, 6, 7. So 7 mountains means a multiplicity of 7, so a septet. But now here's the thing. If you have a multiplicity of 7, well, that means you have 6 neighbors. So number of neighbors is equal to the multiplicity minus 1. So the number of neighbors is equal to 7 minus 1, so equal to 6. So this pink hydrogen has 6 neighbors. Do we see the trend here? A blue 6, and our other peak has an integration of 6. Okay. So the next thing I want to look at is the ppm. So this ppm is about, we could say like 4.4. And on the ppm scale, ppm, things up here are electron rich. Anything down here would be electron poor, and it's all relative to one another. So what do I know about this hydrogen, the pink hydrogen, in summary? I have one H, and if it's connected to a carbon, and it has 6 regular neighbors, the neighbors are going to be J3 away. So what does this mean? Well, if I start at this hydrogen, and I count the number of bonds, 1 bond, 2 bond, 3 bonds, gotcha. This would be a J3 away. So the pink hydrogen and the blue hydrogen would be J3 away, so 3 bonds away from one another, and they would be neighbors. And now this pink hydrogen, though, we know it's electron poor. This is electron poor. What does this mean? Well, look at our molecular formula. Is there any electron withdrawing groups? Well, there's a bromine. Bromine is an electron withdrawing group. So that means if bromine's attached to the same carbon as potentially this pink hydrogen, well, what would that do to the electron density of the pink hydrogen? It would make the pink hydrogen electron poor. So if the bromine was right there, sucking electrons away from this carbon, well, consequently, this pink hydrogen would also become more electron poor. Hence, it would appear, the peak, at a higher ppm value. So I'm going to guess, well, the bromine is going to be also attached to the same carbon as the pink hydrogen that has an integration of 1 that is electron poor. All that's left to do is solve the imp for the blue. So I have imp integration is equal to 6. So I'm like, do I have a carbon that could have 6 hydrogens? Let's see. Connected to 1, 2, 3, 4, 5, 6. Well, no, this breaks the octet rule. Breaks the octet. Bad. A carbon can only make 4 bonds. So at most, we could have a carbon with 4 hydrogens. I'm going to show you a little trick. So if the integration is equal to 1, what does this mean? Well, it means you have a CH. So a hydrogen attached to a carbon. If your integration is equal to 2, well, we're most likely talking about a CH2. If your integration is equal to 3, we're talking about a CH3. So now let's times all of these integrations by 2. Times by 2, times by 2, times by 2. Well, 1 times by 2 would still be an integration of 1, so nothing changes. 2 times 2 would be an integration equal to 4. And 3 times by 2 would be an integration is equal to 6. If the integration is equal to 4, well, what does this mean? This means you have 2 CH2 groups that are equivalent. If your integration is equal to 6, well, that means you have 2 CH3 groups that are equivalent. So this would be case 1, case 2, and case 3. And then case 2 prime and case 3 prime. So we have case 3 prime. We have integration equal to 6, so that means we have 2 CH3 groups that are equivalent to one another. So think about, for example, propane. If you split this structure directly in half, well, these 2 pink carbons would be equivalent. So that means the hydrogens attached to each of these carbons would also be equivalent. So the integration for the pink hydrogens would be not 3, but 6, because there's 6 hydrogens that are exactly the same. So I kind of just gave away the answer there, but this means we have CH3 times by 2. So I could have also wrote this pink hydrogen as a CH group rather than just an H. So the multiplicity here is equal to a doublet, so 2. So how many neighbors? 2 minus 1. Therefore, 1 neighbor. Who's the one neighbor? Well, it has to be a hydrogen. And then the ppm, well, this is like 1.9, so this is electron rich. So taking this information and the molecular formula and the DBE, let's get a new page and then solve for our final structure. So starting first with the DBE information, how can I relate this back to the molecular formula? Well, DBE is equal to 0, meaning that there is no double bonds and there is 3 carbons. So how can I arrange these 3 carbons for them to not have any double bonds? Well, one of the arrangements is going to be propane. So let's work with this. So now I have my 3 carbons. C3 are all accounted for. 1 carbon, 2 carbon, 3 carbon. So taking my, on the right-hand side, whole molecular formula, I'm going to start subtracting off what I know. So minus C3. So what am I left with? I'm left with H7Br. Now working with the pink, we have an integration of 1. So 1 hydrogen. Where should we put it? Well, what if we put it right in the middle here? 1 hydrogen. And the thing with solving an NMR spectra is that you can solve it wrong and then revise your answer and make a new guess. But these questions are usually out of 10 or 12 marks, and usually the answer is 1 or 2 marks, and doing all of this, doing integration, multiplicity, ppm, DBE, electron poor, electron rich, identifying all of those things would be worth the other 10 marks. So you've already got 90% of the question right if you've done just this. If this carbon would make a total of 4 bonds, right now how many bonds has it made? It has 1, 2, 3 bonds, right? And we were told that the pink hydrogen is electron poor, so we hypothesized that the bromine group was also attached to this carbon. And if that's the case, well, bromine, then this carbon, the green carbon, has 4 bonds, and we're done with it. So let's try this. So I'm going to subtract off minus NH and minus Br. So what am I left with? I'm left with H6. Where could I put these 6 hydrogens? Well, what carbons need bonds? This carbon needs 3 bonds. And this carbon needs 3 bonds. And this would be our final structure. And now we can work backwards and see if we did this right by looking at the product. This product, and you were asked to draw the NMR spectra, we should be able to come up with the exact same one if we did this correctly. So let's do IMP. So find the unique hydrogens. So the pink hydrogen. What's the integration? Well, how many pink hydrogens are there? Integration would equal 1. Multiplicity, well, how many hydrogens are J3 away? Starting from the pink hydrogen, we have 1 bond, 2 bond, 3 bond, gotcha, 1. 1 bond, 2 bond, 3 bond, gotcha, 2. 1 bond, 2 bond, 2 bond, 3 bond, gotcha. 1 bond, 2 bond, 3 bond, gotcha. 1 bond, 2 bond, 3 bond, gotcha. 1 bond, 2 bond, 3 bond, gotcha. I hope you're seeing the vision here. So this would be 6. We would have 1, 2, 3, 4, 5, 6 neighbors. So the neighbors is equal to 6. And what did we say? Multiplicity is equal to the neighbors plus 1 because the neighbors was equal to the multiplicity minus 1. So neighbors, the multiplicity is going to be 7. So septet, which is what we had. And now the ppm, well, this should be electron poorish because there's a bromine group attached to the exact same carbon as the pink hydrogen. So CH groups with an electron withdrawing group should appear around a ppm of 4. Let's do this again for the blue hydrogens. So now when we talk about the blue hydrogens, for the integration, we're referring to all of them. So the integration is going to be all of the hydrogens that are in the same chemical environment. So if I split this molecule in half, chop it vertically in half, well, then these two groups are exactly the same. They're in the same chemical environment, meaning that their integration is going to be collective. So the integration is equal to 6. But now for the multiplicity, you cannot be a neighbor with yourself, right? If you live in a house, you're not your own neighbor. You're only neighbors with the people that live in different houses than you. So the multiplicity of any one of these hydrogens is going to be the same. So you just have to focus in on one. So I'm like, what's the multiplicity of this hydrogen? How many other hydrogens that are not blue hydrogens are 3 bonds away? 1 bond, 2 bond, 3 bond, gotcha. Well, there's only one neighbor. So what's the multiplicity? It has to be 2. Multiplicity is equal to 2 because neighbors is equal to one neighbor. And then multiplicity is going to be the neighbors plus 1. So 1 plus 1 is equal to 2. And now for the ppm. The ppm of these blue hydrogens, well, they're on a blue carbon, and this blue carbon is not attached to anything that electronegative. There's no electron withdrawing group directly on the same carbon as any of these blue hydrogens, so they should be quite electron rich. And CH3 groups usually appear, if they're electron rich, from 0.5 to 2 ppm at max. And now if we take this information and we look at the original spectra, case, we have one hydrogen here, and we have the 2 CH3 groups here, times 2, and then the CH times 1. This corresponds to this, and that corresponds to that. Alright guys, I hope this video was helpful. I'm going to be doing a series of solving NMR spectrums. I hope this video was helpful. Let me know if you have any questions in the comments section. And I hope you have a great day. Keep slaying and keep studying on. Chemistry is very, very fun if you practice. Hopefully you'll see the joy in it that I do as well. And please make sure to leave a like, comment, save, and or subscribe to my channel if you did watch this entire video. It really does help out the channel. Okay, thanks. Have a great day. Bye.